Here are solutions to homework set number 11 for ECE 461-661 Control Systems. This homework set looks at digital PID control. So the first problem is, suppose I have an analog system, G of S, with poles at minus 0.47, minus 3, minus 9, minus 16. Design a digital I compensator that gives you 20% overshoot for a step response. Simulate the closed loop system using your favorite language. I'm going to be using MATLAB. To design it, I'm going to use the alternate approach. I'm going to have my G of S. I'm not going to convert to the z-plane. I'll keep G of S the same. I'll have a half sample delay. So if the sampling rate is 0.5 seconds, I'll have a half sample delay. And then my integrator, kz over z minus 1. Now what I'm going to do, I'm going to search along the damping line for 20% overshoot, search along the line minus 1 plus J2 times alpha till the angles add up to 180. When I have S, I'll plug it in for S. To get Z, I'll do Z is e to the st. Keep going until the angles add up to 180. When I do that, time passes. Eventually, the point in the S-plane is minus 0.18 plus J.37. And the Z-plane, that's where it is. Analyzing everything, angles add up to 180. Gain's wrong. Pick K to make the gain 1, so K is 0.277. So here's K of Z. Now to check the answer, I'm actually going to write a MATLAB program to do that. The way I'm going to do that is, here's my G of S. I'll input that into MATLAB and then pull out the corresponding ABCD matrix. In my code, I'll have sampling rate of 0.5 seconds. So in the code, I'm going to be running every 0.5 seconds, I'm going to call this routine. The discrete time compensator is, this is 0.27 z over z minus 1. So it says the next input is the old input, that's the z minus 1, plus 0.277 times the input. The input is the error difference between r minus y. That gets updated every 0.5 seconds. Meanwhile, the system is actually running sampled every 10 milliseconds. I'm going to use numerical integration. So here's your x dot equals ax plus bu, y equals cx plus du. U is only updated every 0.5 seconds. That's my discrete time compensator. But the plan is analog. Not the world's best form of integration. I'm using Euler integration. But keep dt small, it's not too bad. And save the results every 10 milliseconds. Now when I do that and plot it, here's what I get. I can see the input is changing every 0.5 seconds. There's my discrete time u. Here's the output y. Y is analog. I designed for 20% overshoot. And sure enough, I've got just about 20% overshoot. A little bit more because my integrator, I'm using Euler integration. But that basically checks your design. It is working. That's an I compensator. Problem 2, design a PI compensator. In this case for PI, I've got a 0 I can put anywhere I want. I'm going to pick it to cancel that pole, the slowest pole. Well, the slowest pole in the S-plane is minus 0.47, mapping to the Z-plane, 0.79. So here's the form of my compensator. Cancel the slowest pole, replace it with a pole at plus 1, integrator. Have the half sample delay for the sample and hold. G of S, search until the angles add up to 180. Now the point in the S-plane that does that is at minus 0.7 plus J1.4. The spot in the Z-plane. Analyzing G times K times delay, I get 180 degrees. That's good. Gain's wrong. To make the gain 1, K is 3.69. So this is K of Z. That should give me a faster system with 20% overshoot. Now checking it in simulation, here's my new K of Z. Again, this is 3.69, z minus 0.9 over z minus 1. This is the z minus 1. U is the old u, plus 3.69 times z minus 0.79. So the first one is the current error. Here's the previous error. That ratio tells me where I put the 0. The 3.69 puts me at that spot in the root locus for 20% overshoot. Try it. So this updates the input every 0.5 seconds. Here's the analog system, updated every 10 milliseconds. Run it for 9.9 seconds, and here's what I get. So here's the input U. You can see the 0.5 second sampling rate. Here's the output Y. There's my 20% overshoot, about. So a little bit off. And again, this isn't a second order system. And my Euler integration isn't the world's best, but not too bad if you keep the sampling rate small, or step size small. Basically, meets the specs. Problem 3. Design a PID compensator. Now with a PID, I've got two zeros to place. Pick one to cancel the slowest pole, the second to cancel the next slowest pole. Well, the slowest pole is at 0.47, meaning 0.79 in the z-plane. The second pole is at 0.18 in the z-plane, so there's my compensator. Pick K so that I'm on the damping line. So search the damping line until angles add up to 180. It turns out the point that hits it is 0.88 plus J 1.77, corresponding spot in the z-plane. Analyzing at that spot, pick the gain, K to make the gain 1. K is 5.09, so here's K of Z. To check my answer, I'll multiply out the numerator, denominator polynomials. So here's my system. I'll remember the current error, one sample ago, two samples ago. Here's the numerator polynomial, 5.09, z squared minus 0.96z plus 0.144. That shows up right here. Let that puppy run for 10 seconds, and here's what I get. Once again, 20% overshoot, close. Here's my input U. There's the output Y. Problem 4. If I want to meet some design specs, like I want the settling time to be 10 seconds, what that means is in the S-plane, I want the dominant pole to be at minus 0.4 plus J 0.8 for 20% overshoot. For T is 0.5, here's the corresponding spot in the Z-plane. I'll pick K of Z in this form. Cancel the two slowest poles, add a pole as equals 1. This one I'll slide around to make the angles add up. Analyze my design point. This is G of S, half sample delay, K of Z. Angles have to add up to 180. Plug in what I know. The angle's off by 58 degrees. So the term that I left out, C minus A, that has to contribute 58 degrees phase shift, telling you that A is 0.55. So here's the form of K of Z. And my design point angles add up. Gain's wrong. Pick K to make the gain 1, so there's K. Here's K of Z. Multiplied out. I can implement that in code. Remember the current input, one sample ago, two samples ago. Current error, one sample ago, two samples ago. The numerator polynomial goes right here. The denominator polynomial goes right here with a sign flip. Run that puppy, and I get a 10-second settling time, 20% overshoot-ish, and discrete time system. Finally, if I change the sampling rate, well, if I change the sampling rate, I grumble because that means I have to do complete redesign. Well, if I change the sampling rate, same spot in the Z-plane, my design point in the Z-plane is now totally different. My compensator is cancel the two zeros just like before, but T changed, so the zeros changed. Analyze what I know, and my design point, angle should add up. I'm up by 55 degrees, so A should be 0.9048. Analyze what I know, angles are 180, gain's wrong, so here's K of Z. If I try it, multiply out the numerator, denominator polynomial. The numerator polynomial shows up right here. Denominator polynomial shows up right there. Run it with sampling rate of 0.1 second. And we see as the input changes every 0.1 second, of course, 20% overshoot, 10-second settling time. Pretty much meets the specs. So that's homework set number 11 for ECE 461.